So, ladies and gentlemen, it's my great pleasure to welcome today Quoc Lu, who is a PhD student with the Université de Toulouse in France. And he's been a bachelor student in mathematics at Ho Chi Minh City University in Vietnam, where he did his bachelor degrees in mathematics. Afterwards, he received his master's degree from the University in Toulouse in 2018. And currently, as I already mentioned, he's a PhD student in Toulouse, and his main research aspects are Kalman filtering, fault detection and isolation, and especially in combination also with interval tools when system models with bounded parameter uncertainty are concerned. And this is also the area where today's presentation will come from. Quoc will now talk on interval Kalman filter enhanced by lowering the covariance matrix upper bound. Quoc, the floor is yours.
Thank you for your introduction. Hello everyone, my name is Quoc Lu. I'm a PhD student at University of Toulouse, and I'm working at LAAS-CNRS laboratory. Today, I'm pleased to present to you our work entitled Interval Enhanced by Lowering the Covariance Matrix Upper Bound. In this talk, I will introduce the improved minimum upper bound of variance interval common filter, IUBIKF. The proposed method is developed based on an uncertain discrete-time linear model with additive Gaussian measurement noises. The model is also subject to bounded parameter uncertainty in state and observation matrices and in the covariance matrices of the Gaussian noises. We call this context the mixed uncertainty. This is a combination between the stochastic uncertainty and the bounded uncertainty. The proposed methods consist in using the spectral decomposition of a symmetric matrix to provide a less conservative error covariance upper bound than the one provided by the UBIKF proposed in Tran et al. 2017. An academic numerical example is used to show the efficiency of the proposed methods with respect to its precedent, UBIKF. Also, a comparative analysis between the proposed methods and the one proposed in Raka and Compastel 2013 is proposed by simulating a two-wheel vehicle model, an application in automotive domain. Since the proposed method is a kind of interval filter, so the interval computation is a main tools to develop this filter. I will present some preliminaries of interval analysis and related result. A real interval will be denoted by bracket of smaller x, which is a closed and connected subset of R. A real interval matrix is denoted by bracket of capital X, which is a matrix whose elements are real intervals. Define also the supremum matrix of bracket of X, the infimum matrix of bracket of X, the midpoint matrix of bracket of X, radius matrix of bracket of X, as elements-wise operator applying to the interval matrix X. And we also denote respectively these matrices by overlines X, underline of X, XM, and XR. The proposition 1 proposed in Tran et al. 2017 give a representation of matrix M belonging to a given interval matrix bracket of M. The proposition says that there exists M by N real value alpha ij between -1 and 1, so that the matrix M can be expressed in the form of the equation 1 here, in which the MRIJ is a matrix whose elements are 0, except that its ij's entry take the value of the radius of the ij element of the interval matrix M. And if the matrix M and the interval matrix are both symmetric, the proposition 2 says that there exists an n by n plus 1 over 2 real values alpha ij between -1 and 1, so that the matrix M can be expressed in the form of the equation 2, in which diag MR is a diagonal matrix containing the radius of diagonal elements of bracket of M. And diag alpha II here is a diagonal matrix with alpha II issued from the n by n plus 1 over 2 real value alpha ij aforementioned. And MRij Ji is a matrix, is a symmetric matrix whose elements are 0, except that its ij and Ji entry are equal and take the value of the radius of the ij elements of the interval matrix M. Now we go to the notion of upper bounds of matrices and related result. A positive semi-definite matrix will be denoted by M greater than or equal to 0. For two real square matrices of the same dimension, M and N, M is called an upper bound of N if and only if M minus N is a positive semi-definite matrix. The proposition 3 proposed in Tran 2017 provides a set of upper bounds according to the choice of parameter beta of the form Mn transpose plus Nm transpose for any two non-null matrices M and N with the same size. Proposition 4 proposed in Combustel 2016 says that for any symmetric matrix M with its spectral decomposition V, D, V transpose, let M plus determined by V absolute value of D, V transpose, then the matrix M plus is a positive semi-definite matrix and it is an upper bound of all matrix alpha M for any alpha take value between -1 and 1. The proposition 5 developed in this work says that there exists a symmetric positive definite matrix S, which is an upper bound of the form MPM transpose for any real matrix M belonging to a given interval matrix, bracket of M, and P a symmetric positive definite matrix. The expression of the matrix S can be determined by using proposition 1 and 4. Proposition 6 also developed in this work says that there exists a symmetric positive definite matrix M plus, which is an upper bound of all symmetric matrix M belonging to a given interval symmetric matrix bracket of M. And the expression of the matrix M plus can be determined by using proposition 2 and 4. Now we go to the problem formulation by considering the following discrete-time linear system in which xk are state variables, yk measurements, uk inputs, wk state noises, and vk measure noises. The parameter matrices ak, bk, ck are assumed to be unknown deterministic and belonging to no interval matrices. Wk and vk are standard Gaussian with covariant matrices qk and rk belong to no interval matrices. The initial state x0 is assumed to be standard Gaussian, and finally x0, w1 to wk, v1 to vk are mutually independent. Now let's take a look at some reviews of the standard common Fillter also called the conventional common filter. To recall some notation which will be used the next. The standard common filter provides the minimum variance estimate x hat kk of the real state xk with the associated covariance matrix pkk. The notation x hat k minus 1 is used to denote for the a priori state estimate vector at time k given observations up to time k minus 1, x hat kk, the a posteriori state estimate vector at time k given observation up to time k, pk k minus 1, the a priori error covariance matrix, and pkk, the a posteriori error covariance matrix. The standard common filter also assumes that the initial state x0 equal to x00 and the error covariance matrix p0 equal to p00. The proposed method is developed from the interval common filter introduced in Tran et al. 2017, namely UBIKF. It's aimed to obtain a less conservative upper bound P plus KK of the state estimation error covariance than the one obtained by the UBIKF. And the improved filter can be designed in 2 steps, prediction step and correction step, similarly to the structure of the standard common filter. In the prediction step, assuming that the real state x0 is included in the estimate interval x has 0, 0, and the error covariance p0 is upbounded by p plus 0, 0. The prediction step performs similarly to the standard common filter using the natural interval extension as expressed in the equation 7. Then we have to find the upper bound p plus k minus 1 of this term for all ak in the interval a and qk in the interval q, in which p plus k minus 1 is the upper bound of the posteriori covariance matrix at the previous time instant k minus 1. Using proposition 5, we get the upper bound of the first term, and using the proposition 6, we get the upper bound of the second term. And the matrix P plus K minus 1 is determined by the sum of the 2 upper bounds. In the correction step, the a posteriori state estimate interval x has k is obtained by computation using the natural interval extension of the standard common filter as expressed in the equation 10. This expression can be rewritten in the form of the equation 11 in order to reduce the effect of the dependency problem of the interval computation. In the expression, kk is again matrix. Given that x hat k minus 1 belongs to the interval x hat k minus 1, we get the x hat k will enclose all possible value of x hat k. The again matrix kk is determined as follows. First, we denote this term by pkk as the error covariance matrix after the correction step. Then we find the upper bound p plus kk of this term for any ck in the interval c and rk in interval r. And finally, the again matrix k will be chosen as the minimizer of the trace of the P plus KK, where this term is a function of the again matrix KK. To find the upper bound P plus KK, we use the proposition 1 to decompose the matrix C into this form and apply to the expression of PKK. Then we get the following terms. And we have to find the upper bound of each of these terms. And finally, the expression of the matrix P plus KK is the sum of these upper bound. The first term in blue here is hold. The second term in blue here is upper bounded by a similar form with the coefficient 1. The last term here is upper bounded by the similar form with the coefficient 1. And then the bracket will be upper bounded by a matrix S, ML, IJ using the proposition 4. And also we use the proposition 6 to find the upper bound R plus of the matrix RK. So finally, this term is upper bounded by a similar form with the coefficient 1, and then the bracket in red will be upper bounded as follows. The first term of the bracket is rewritten in the form of XY transpose as here. And the second term is the transpose of the first term. So we use the proposition 3 with beta equal to 1 to get this kind of upper bound, XX transpose plus YY transpose. And finally, we get the expression of the upper bound P plus KK. In this expression, N0 is the number of interval elements of the matrix C. The again matrix K is chosen as the minimizer of the trace of P plus KK. Basically, it is the solution of the equation, the derivative of the trace P plus KK with respect to K equal to 0. And with this choice of GAN matrix, the error covariance upper bound has the simplest form expressed as here. Now we go to the academic example by considering the following system without input UK. And we assume that the parameter matrices AK, CK, QK, and RK belongs to the following interval matrix C. In this system, the state vector xk has 3 dimensions. Each of its components correspond to one state in consideration of the system. So in this system, we have 3 states, x1, x2, and x3. We simulate in 1000 iteration and using the toolbox in lab of MATLAB. In this example, we will compare the estimation result provided by the 2 filters, and the following performance evaluation criteria are used. The first one is the root mean square error upper bound, denoted by the overlay of RMSEs, defined by this expression, in which square and square root are element-wise operator, and L is the number of iteration. The second one is the percentage O, where the confidence interval ICK contains the corresponding real state XK. the confidence interval ICK is defined by the estimate interval x has kk plus this interval vector, and it will be called the 3 sigma confidence interval in the next. The following figure shows the estimation result related to the state x1 with corresponding 3 sigma confidence intervals provided by the two filters. We see that state x1 belongs to the two confidence interval provided by the two filters. So the all percentages are 100% for the two cases. And we also see that the confidence interval provided by the improver filter is smaller than the one provided by UBIKF. The same result for the state X2 and X3. The table 1 summarizes the comparative evaluation of the three states X1, X2, X3 here. We see that the all percentages are always 100%, and the RMSEs provided by the improved filter are smaller than the ones provided by the UBIKF. The disadvantage of the improved filters is the computation time. Now we want to compare the error covariance upper bound provided by the two filters with a reference to the error covariance provided by the conventional Kalman filter. We do as follows. We simulate 1,000 times of parameter matrices AK, CK, QK, and RK uniformly from corresponding interval matrices. Then we compute the error covariance PKK for each of simulation time, and the maximum value of diagonal elements of these matrices are used afterward. For example, we compare the maximum value of the 1,1 elements of these matrices with the corresponding upper bound provided by the two filters here, and we get the result. The upper bound provided by IUBIKF on the one hand is less conservative than the one provided by UBIKF, and on the other hand is close to the maximum value provided by the standard common filter. And the same result for the two other elements P22 and P33. Now we go to the case study from the automotive domain. It is a continuous time nonlinear model of the dynamics of a two-wheel vehicle that has been linearized and discretized. The resulting state space model has two states. X1, the angular speed of the side slip angle, and X2, the acceleration of the vehicle yaw. In this simulation, we will compare the estimation result from the three filters, IUBIKF, UBIKF, and the interval observer proposed in Raka and Compastel 2013. The following figure shows that the real value X1 or X2 here are always included in the three state interval estimate provided by the three filters, in which the estimate interval provided by the improved filter IUBIKF is the tightest of the three. And table 2 shows the RMSE index with respect to the two state X1, X2 in the three cases. We see that the RMSE provided by the improved filter is smaller than the other two methods, while the computation time is greater. To conclude, the improved minimum upper bound of variance interval common filter IUBIKF is proposed in this research. It provides a lower error covariance upper bound, and it also allows to bound the set of all possible state estimation given by the common filter for any admissible parameter uncertainty. This filter is intended for system of moderate dimension, and so it has not been optimized for larger system. This work shows that the integration of statistical and bounded uncertainties in a same model can be successfully achieved, which opens the perspective from a practical point of view. I finished my talk, and thanks for your attention.
So many thanks, Quoc, for your very interesting presentation. And before we open the floor for discussions, maybe one comment from my side. I think it's really, really very important that someone is trying to get those two different worlds, the stochastic interpretation of uncertainty and also the bounded or set-valued interpretation of uncertainty, to get those different representations into a joint estimation framework. I think yes, treating those different types of uncertainties completely separate, as many people are doing, is certainly not the only thing. And from that perspective, I think your contribution is really very welcome to the community. Now, who wants to start with questions?
I have a simple question.
Yep, please go ahead.
Do you need to solve LMIs at every step?
Yes. What you mean?
In your method, at every step, I think you need to solve linear matrix inequalities, right?
Sorry, I don't.
The question has been whether you have to solve linear matrix inequalities at each discretization step.
In the you say that in the upper bounded to find the upper bounded matrices, is that?
Yes, whether yes, you're solving LMIs there or not.
How to solve your gain matrix KK at each step? At each step,
the gain matrix KK. You
yes.
So this form of expression is analytical expression you can find at each step.
Yes, and I think also the matrix P plus is an analytic expression and not the solution of a numerical LMI-based optimization.
How to solve this P plus K minus 1?
Yes, this is here in the prediction step. You can find the P plus K minus 1 for this term.
do you need to solve this LMI in equation 8? I think it's an LMI problem.
I don't know what RLMI you say.
Linear matrix inequality.
Yes. Now in this development, we use the proposition 5 and 6 aforementioned. From you see that is use the decomposition of the matrix M in the interval M, and then we compute with this form, and then we use these two propositions to get the upper bound.
Yes. Maybe you do not use LMI, but you use some other algorithm.
Yes.
In each,
okay, I see.
Yes. In
Thank
each
you.
each step, we have analytical expressions of matrices. We can see it in the algorithm. Sorry, I'm Karine Joberti. Quoc, could you find the algorithm, please?
Algorithm.
Yes.
Algorithm.
In a slide.
No, I'm not. I'm not get algorithm in the slide.
Yes. It is given in the paper.
Yes.
Yes, but maybe this opens up one question from my side, because as Karine just said, you have an analytic representation of the matrix. And as far as I understood it, you restricted yourself to the case that the parameter beta was set to 1.
Yes.
Yes, and you have more or less infinitely many solutions that are overbounding this inequality that you had shown before in the proposition 5. So
yes.
The question is, did you try to, let's say, I think it doesn't make sense to do this in each time step, but maybe in advance for some specific problem to use beta as some additional degree of freedom in order to optimize the solution, let's say to find a further degree of freedom in order to reduce the pessimism of your confidence bounds?
We have a research related to the optimizer, but first we must define the optimization in which sense, and in that research we have defined that the optimized upper bounds is based on the norm minimization, and the optimized upper bounds is determined, but don't have a analytical expression, but we can use a very simple form of this kind of upper bound, that is on scalar alpha k multiplied by the identity. So it's give the very advantage in the computation and also in the meaning of the upper bounds.
Okay, I see. Yes, maybe if we don't have other questions at the moment from the audience, let me continue with a further question. Could you go to the slide? I think the slide 27, where you had this nonlinear bicycle model. Then it was the 28, the result. Yeah. Yeah. My question there is, your Kalman filter approach, I think, uses a purely linearized system model.
Yes.
And the linearization, if I got it correctly, was being done at the last estimate of the expected value. Is this correct? that you get a point-valued approximation of your nonlinear system model.
You mean that a point approximate?
Yes, the question is, how did you approximate your nonlinear system model? Because you have sine and cosine terms as nonlinearities, and those are multiplied with a velocity component. That means you have to linearize at least 3 nonlinearities in the system model, trigonometric functions and products. And the question is, after the linearization, do you have a point-valued system matrix, the matrix A in your linearized model, or is this directly an interval matrix? And if it is an interval matrix, how you did the computation?
The linearization give the matrices, I said A, D, C, D, and in B and D also in this example we have used the input UK also, and from these matrices we simulate the interval matrices, corresponding interval matrices by using the unit matrices as its midpoint, and afterward we take a radius around this midpoint to use.
How do you determine this radius? Because my question is this radius related, if you have an interval matrix there, is this radius related to the covariance estimate that you have?
It's just a heuristic choice, but related to too many experiments. And
okay, then maybe it would be a good option to look at a preprint that I just added, I think 2 or 3 weeks ago, to my ResearchGate profile, because what I did is I computed, let's say, interval bounds or also ellipsoidal bounds for system models that are nonlinear. And yes, I had an application scenario in which I did, let's say, some kind of robustness analysis of a linearization-based filter algorithm. That means an extended Kalman filter in this case. And I think this would be a good opportunity to use such a procedure to define some kind of interval Jacobian matrices that are directly related to the confidence bounds produced by your filter. And this would lead to, in each sampling step, to new interval bounds for your system matrix A.
Yes.
I think this would be a more fair comparison. And maybe also concerning the interval observer approach that you have there. Does this interval observer, I'm not exactly sure which paper of Christophe Combastel you are quoting here. Does this observer assume that your system dynamics are cooperative? That means that your system model is a Metzler matrix?
This is a interval observer to continuous time, and it used the additive and also the multiplicative disturbance in the assumption.
Okay, I'll have a further look at this paper. Yes, and then we could go to, yes, I didn't write down the slide number. It was the first example where you had the matrices A and C on one slide.
Yeah.
The numeric values. Yes, here. Those numeric values, I think the diameters in the matrix A and the matrix C are very similar. You have interval diameters, let's say, in the order of 0.1 in both matrices. My question is, does it make sense to perform some kind of change of coordinates, either to try to get the matrix A close to a diagonal matrix, or to try to get the matrix C close to a diagonal matrix in order to reduce the wrapping effect that you typically have in interval evaluations?
I think it's maybe a nice proposition, and we can find an experiment with this. But in this choice, we can see that we have a liberty to choose the interval matrix, and almost all we don't care much about the constraint in these in interval matrices.
Okay, do we have any further questions from the audience? Yes, if not, I have a question as an outlook. Your matrix at the moment is a purely parameter dependent matrix, the matrix A and the matrix C. And just because you're working in a discrete time framework, I think it's no real problem that even the parameters may change from one time step to the other. You just have to replace the matrices by new numeric values. The question is, did you consider or do you aim at using scenarios also where the matrices are really state dependent, that you have some matrix A of X, C of X times X? Do you aim at treating such scenarios in the future, or what is your proposition how to go on into this direction?
It will be a nice proposition, and it will out of the framework of the interval Kalman filter. So I say it may be for the first thing is nonlinear, and maybe use other methods very different from that we propose here.
Okay, do we have anyone in the audience who either wants to ask questions, to comment? So if this is not the case, I'll thank you again, Quoc, for your interesting presentation, also for your patience to answer all the questions at the end. And yes, from my side, it's now time to wish you a nice Friday afternoon, evening, weekend as usual. But now the break will be a little bit longer as usually, because we are now going into our summer break. And at the moment, the point of time when we are restarting the seminar series is not yet completely fixed, but it will be either at the end of September, beginning of October. You'll get an invitation again to our mailing list, and hopefully you have a nice summer holiday and see you soon, and stay healthy.